Understand the underlying chemistry principle. Beer's law states that the absorbance A of a solution is directly proportional to its concentration C when the path length and wavelength are held constant. A equals epsilon BC because of this direct, linear relationship. As the concentration of a chemical species increases, its measured absorbance must also increase in a highly predictable, linear fashion. Examine the provided standard calibration data. Look closely at the recorded values in the student's table. At 0.025 molar, absorbance is 0.059 at 0.050 molar. Absorbance is 0.235 at 0.100 molar. Absorbance is 0.117 at 0.200 molar. Absorbance is 0.468. Identify the anomaly in the data. Comparing the 0.050 molar and 0.100 molar entries, the concentration doubles, but the recorded absorbance bizarrely drops by half, from 0.235 down to 0.117. This non-monotonic behavior directly violates Beer's law, indicating a major error in the preparation or recording of those specific standards. Test the hypothesis of reversed cuvette labels. Let's check what the data looks like if we assume the student accidentally swapped the labels on the 0.050 molar and 0.100 molar cuvettes. For 0.025 molar, absorbance over concentration equals 0.059 over 0.025 is equal to 2.36 for 0.050 molar. Using swapped value 0.117 over 0.050 is equal to 2.34 for 0.100 molar. Using swapped value 0.235 over 0.100 is equal to 2.35 for 0.200 molar. 0.468 over 0.200 is equal to 2.34. Conclude the correct option. Because the ratio of absorbance to concentration becomes beautifully constant, approximately 2.35, across all data points when we swap the 0.050 molar and 0.100 molar values, it is highly likely that the student accidentally swapped the labels on these two cuvettes. This matches option C. The correct answer is option C. The student labeled the cuvettes incorrectly, reversing the labels on two of the solutions of known concentration.